Hello, my name's Matt Bell. I'd like to welcome you to the first of a 6-part video series brought to you by Hart Energy and Geodynamics, which will discuss the techniques and technologies involved in wellbore perforating. In part 1 of the series, we'll discuss how perforating fits into the overall well construction process. I'll run through the key design choices that the completion engineer must make when selecting a perforating system, and explain how the latest perforating technology is helping to make wells more productive and more profitable. When the drilling operation has reached its targeted depth and open hole formation evaluation has been completed, the next step is usually to run a steel casing to bottom and cement it in place. This supports the borehole, preventing it from collapsing during the producing life of the well. It also provides a barrier to flow, isolating potable aquifers and other potentially sensitive formations from the oil or gas bearing strata. The cemented casing forms a secure conduit from the reservoir to the surface. Now it must be connected to the rock layers from which hydrocarbons will be produced, or where gas or liquids will be injected in the case of an injection well. This is where perforation comes into play. The overall objective when perforating is to create an effective flow path between the wellbore and the formation of interest. It's important to remember that creating a hole isn't necessarily the same as creating a flow path. The perforation tunnel must be free from debris and extend into undamaged reservoir to satisfactorily conduct flow into or out of the well. Carriers, known as guns, loaded with shaped explosive charges, are lowered into the well and positioned across the zone of interest using gamma ray and casing collar locator tools to ensure accurate deployment. In a vertical or moderately deviated wellbore, this operation is normally performed using wireline. When the wellbore is highly deviated or horizontal, or when the perforating assembly is too long to be deployed on wire, coiled tubing or jointed pipe will be used to push the guns to the required depth. Alternatively, if communication has already been established with the formation, the guns may be deployed on wireline and pushed to the targeted depth by pumping fluid from surface. Once the guns are on depth, the explosive charges are triggered by sending either an electrical signal through the wireline or using a mechanical or pressure-activated firing system when deployed on tubing. Depending on the mechanical configuration of the well and the type of perforating system being used, the spent perforating guns will either be retrieved to surface for disposal or dropped to the bottom of the well. After completing as many runs as necessary to perforate the entire target interval, the perforating operation is complete and the well can be made ready for the next operation, usually stimulation or production. Several different perforating systems are available to suit different well conditions, configurations, and formation characteristics. Exposed systems, often referred to as strip guns, are used when the perforating assembly must pass through a significant restriction within the wellbore, such as when perforating through production tubing. Each shaped charge is fitted with a pressure-tight cap so that it can be exposed to wellbore fluid without inhibiting the explosive. These are known as capsule charges. Exposed systems help to maximize the explosive load that can be conveyed in spite of the wellbore restriction. However, their limited mechanical integrity means only short lengths can be deployed, and they should not be pushed into deviated or horizontal wells. Exposed systems also leave a lot of debris in the wellbore after detonation, which can be problematic during production. Hollow carrier systems are preferred for most applications since they offer excellent mechanical integrity and contain much of the debris after detonation, allowing it to be retrieved to surface for disposal. The shaped charges are mounted on a load strip or tube, which is then secured within the gun body. Detonating cord connects with each charge to transmit the detonation along the gun assembly. End plates are used to align the load tube within the gun and prevent it from moving during deployment. In most cases, spot faces, known as scallops, are machined into the gun wall opposite each shaped charge to minimize the amount of energy wasted penetrating through the gun body. Scallops also ensure that any burr formed on the outside of the gun is kept within the overall outside diameter of the assembly, preventing it from damaging the well casing when the spent gun is retrieved. All gun systems are available in a variety of lengths, with individual guns typically ranging from 1 to 21 feet in length. Guns of a different length are often combined in a perforating assembly to accurately perforate the desired interval. Gun diameters range from less than 2 inches for through tubing applications to 7 inches. Charges are typically arranged in a spiral phased pattern within the gun to ensure perforations are created in a variety of directions from the wellbore. Hollow carrier guns are connected in series using tandems. These short assemblies contain bidirectional booster charges that continue the detonating train from gun to gun. To allow several guns to be shot at different depths, pressure-activated switches can be deployed between guns within the same perforating assembly. Special switch subs are used to allow safe assembly and arming of the guns at the well site. The guns are fired in sequence using a combination of positive and negative polarity switches. Several families of shape charge products are available to help fulfill the overall objective of creating an effective flow path. Which type is selected will depend on many factors, including formation characteristics, whether the well will be used for production or injection, and whether the formation must be stimulated in order to make the well economic. Let's talk about the three primary shape charge families: deep penetrating charges, big hole charges, and good hole charges. As their name suggests, deep penetrating charges are designed and optimized to create a tunnel extending as far from the wellbore as possible. This helps to bypass any near wellbore damage caused by mechanical deformation and drilling fluid leak-off during the drilling process. Greater penetration also increases the effective wellbore radius, which leads to greater productivity. Deep penetrating charges feature a conical liner, usually made from a blend of powdered metals that are pressed into shape. When a deep penetrating charge is initiated, the detonation wave collapses the conical liner into a narrow, fast-moving jet of particles traveling at more than 20 times the speed of sound. The jet bulldozes its way through the gun body, casing, cement, and rock, displacing material to the side. This process continues until the jet decelerates below a critical penetration velocity. At that point, its forward progress halts, and the remainder of the jet train wrecks into the end of the tunnel, forming compacted, impermeable debris. In an upcoming future episode, we'll discuss techniques for successfully removing this debris to ensure an effective flow path is created along the full length of the perforation tunnel. Big hole charges are designed to create as large an aperture as possible in the well casing. They're applied when the formation is poorly consolidated and will require the installation of some form of sand control. Under such circumstances, depth of penetration is a secondary consideration because a stable tunnel usually cannot be formed in poorly consolidated rock. Area open for flow becomes the primary concern, since greater inflow area means a lower inflow velocity at any given volumetric flow rate, reducing the risk of hot spotting and erosion of the sand control system. A big hole charge design is generally flatter than a deep penetrating charge and utilizes a parabolic liner, typically stamped from sheet metal. When the charge is initiated, the detonating wave drives the metal liner forwards through the gun, casing, and cement to create a large entrance hole. For many years, all of the commercially available oil-filled shape charges fell into either the deep penetrating or big hole categories. However, the increasing popularity of stimulation techniques, such as hydraulic fracturing and frac compact sand control, fueled demand for something in between. Good hole charges are designed to bridge the gap between deep penetrating and big hole charge families. They're based on deep penetrating designs, re-optimized to deliver a larger entrance hole at the expense of some penetration. Selecting the appropriate type, size, and configuration of perforating system for a particular well application is not a trivial task. While the perforating operation may account for only a small fraction of total well cost, typically less than 1% of the total AFE, the impact of suboptimal perforation on well performance and profitability can be dramatic. In future episodes, we'll discuss how manufacturers generate the performance data found in catalogs, when it is safe to select a system on the basis of those results, and what further steps an engineer can take to ensure the optimal perforating system is deployed in every well. Thank you for joining us for this introductory video in our series on perforation. If you have any comments or questions, please visit Geodynamics' website at perf.com and follow the contact link to reach a Geodynamics representative who will be pleased to assist you.